There's an invisible force that powers pretty much everything around you. I'm talking about the phone in your hand, the lights in your room, even the thoughts in your own brain. It's this deep, powerful, and honestly kind of surprising link between electricity and magnetism. And today we're going to pull back the curtain and see exactly how it all works.
I mean, think about it. What could possibly connect a bolt of lightning to a simple refrigerator magnet? On the surface, they seem like they're from different planets, right? One is this massive, chaotic burst of energy in the sky, and the other is just this quiet little thing holding up your shopping list. But stick with me, because by the end of this, you'll see they're not just related, they're two sides of the very same coin.
So, our story really kicks off back in 1820. There's the scientist Hans Christian Oersted, and he's in the middle of a lecture. And completely by accident, he notices that when he switches on an electric current, a compass needle nearby just twitches. It moves. Now, it might sound like a small thing, but this was absolutely monumental. For the very first time, someone had proof that electricity and magnetism weren't two separate things at all. They were connected. All right, so that twitching compass needle proved it. The electric current was creating some kind of magnetic effect, this invisible field of influence all around it. But that raises a pretty big question, right? How in the world do you map something that you can't even see? Okay, first things first, let's get our terms straight. A magnetic field is just the area where this magnetic force is doing its thing. You can think of it like the heat you feel coming off a fire. You don't actually see the heat itself, but you definitely know it's there because you can feel its effect on your hands. Same idea. So to see this invisible field, scientists came up with a really clever trick: magnetic field lines. These are basically imaginary lines that we draw to act like a map. They show us exactly how the magnetic force is behaving, where it's going, and how strong it is. If you ever did that experiment in school where you sprinkled iron filings around a magnet, well, you've seen these lines for yourself. And this map, it has rules. The lines always flow out of the North Pole and loop back into the South Pole. They always form these complete closed loops. And see how they're packed together in some spots? Where the lines are denser, the field is a whole lot stronger. And here's a big one: they never, ever cross. Why? Well, it's simple, really. A compass can't point in two different directions at the same time. So being able to see this invisible field is cool. But you know what's even cooler? Actively shaping it. This is where we go from just being observers to actually taking control of this incredible force. Let's start with the most basic setup: a straight wire with some current flowing through it. The magnetic field it creates looks like a series of perfect circles, one inside the other, with the wire right at the center. And just like ripples in a pond, the further you get from the wire, the weaker the field gets and the wider the circles become. So how do you know which way those circles are spinning? Clockwise? Counterclockwise? Well, there's a super easy trick for that, and you can do it right now. Go ahead, hold up your right hand. Imagine you're grabbing the wire. If you point your thumb in the same direction as the current, the way your fingers naturally curl around tells you the exact direction of the magnetic field. Pretty neat, huh? Okay, now what if we take that straight wire and bend it into a loop? This is where things get really interesting. Suddenly, all those little circular field lines get bundled together and concentrated right in the middle of the loop. Every single part of that wire is now adding to a magnetic field that's pointing in the same direction at the center, and boom, the field gets way, way stronger. So if one loop is good, what do you think happens if we use a whole bunch of loops? Well, that's exactly what a solenoid is. Seriously, just picture a slinky made out of copper wire. By wrapping that wire into a tight coil, we're taking the effect from that one single loop and we're multiplying it over and over and over again with each turn. And the result is just remarkable. If you look at the magnetic field from a solenoid, it's almost a perfect twin of the field from a regular old bar magnet. You literally can't tell them apart. It's got a clear north pole, a clear south pole, and the field inside is super strong and uniform. We just took a wire and a battery, and we built a magnet that we can turn on and off whenever we want. This is the absolute heart of what we call an electromagnet. Okay, so far, we've seen how an electric current can create a magnetic field. But science loves symmetry. So it kind of makes you wonder, what happens if you flip it around? Can a magnetic field push back on an electric current? So let's picture the experiment. We've got a magnetic field, maybe from a couple of strong magnets. And then we take a wire with electricity flowing through it, and we place it right in the middle of that field. What do you think is going to happen? It moves! The magnetic field actually pushes on the wire. We're talking about a real physical force. And what's even cooler is that it's predictable. If you flip the direction of the electricity, the wire gets pushed in the exact opposite direction. This single idea right here, this is the fundamental principle that makes every single electric motor in the world spin. And you guessed it, there's a hand rule for this too. This time, use your left hand. Point your first finger in the direction of the magnetic field, from north to south. Then, point your middle finger in the direction of the current. Now look at your thumb. Sticking straight out, it's going to show you the exact direction of the force, the direction that wire is going to move. I know this can all seem a little abstract, like something out of a physics textbook. But these principles are at work all around you, every single day, in ways you probably don't even think about. So let's bring this all back home. Let's just peek behind the walls of your house for a second. You've got 3 main wires. There's a live wire, usually red, that brings in the electricity. Then you've got a neutral wire, which is black, that completes the circuit. And finally, there's that green earth wire. That one's a lifesaver. Literally. It's a safety feature designed to protect you from an electric shock if anything goes wrong. Now, the push that actually drives the current between that live and neutral wire is a potential difference of about 220 volts. It's that consistent voltage that reliably powers everything from your toaster to your TV, all thanks to our ability to control these fundamental forces. But this is where the story gets really mind-blowing. This stuff isn't just about technology outside of us, it's happening inside us, right now. Those tiny electrical signals, the little ion currents that travel through your nerves as you think or move or feel, they actually generate their own tiny magnetic fields. Now, these fields are incredibly, incredibly weak. We're talking about 1/billionth the strength of the Earth's magnetic field, but the fact that we discovered them and understood them led to one of the most powerful medical tools we have, the MRI. It uses these exact principles of magnetism to listen to those tiny fields in our bodies, building up these incredibly detailed images of our organs without ever having to make a single cut. And that kind of brings us full circle. We started with a simple twitching compass needle, and we ended up realizing that our very own thoughts create magnetic fields. It's just a powerful reminder that there are these incredible hidden forces all around us, connecting everything in the universe. So the question I want to leave you with is this: what else is out there waiting to be discovered?